Welcome, everyone. Welcome to today's Gold Science Communication webinar. My name is Tom Mason. I'm the Communications and Outreach Manager at the University of Colorado Boulder's Laboratory for Atmospheric and Space Physics. Thanks for joining us today. If you do have questions during the presentation, please use the chat function and I will ensure that those questions get passed along to our speaker today and that she has an opportunity to respond to those. I'll go ahead and introduce our speaker. Dr. Katelynn Greer is a research scientist here at CU Boulder LASP. She studies the near space environment and its connections with the Earth and the lower atmosphere. She earned her degrees, including her PhD, from the Aerospace Engineering Sciences Department at CU, and she completed her postdoc at the University of California, Berkeley Space Science Laboratory. For the GOLD mission, Katelynn is particularly focused on forcing effects from the lower atmosphere by waves and thermal tides. Katelynn, thanks for being here. I'm going to stop sharing and allow you to share your presentation. And just so everybody knows, this will be recorded. I noted that in the chat. And the video and audio, as well as the PowerPoint files, will all be posted on the website in the chat if you want to share that with others who are not able to join us today. Thank you. Katelynn, I'm going to hand it over to you.
Okay, thank you. Let's see here. Okay, does everything look good?
It looks great.
All right.
Thanks.
Again, I'm Dr. Katelynn Greer. Thanks for being here and welcome. Today we're going to talk about some of the ripples that we see in Earth's upper atmosphere, so specifically waves and tides. Before we get started, I want to send out a special thank you to Dr. Federico Gasparini, who really developed a lot of these slides and I've adapted. So to get started, I always like to start with this image. It's taken from the International Space Station, and it's at the limb of the Earth. So that means it's looking at the very edge of the Earth. And what's special about it is you can see the different layers of the atmosphere. So the gold portion is the troposphere. The sort of tan pinkish layer is the stratosphere. And then the blue is our upper atmosphere, our mesosphere and thermosphere. And then when it goes to black, that's kind of what we're thinking of when we say space. So we're going to talk about three main topics today. The first is variability in the thermosphere. And then we'll talk a little bit about atmospheric waves. And then lastly, we'll talk a little bit about how we observe some of these waves in the upper atmosphere. So the atmosphere, as I mentioned before, is made up of layers. We live in the lowermost layer called the troposphere, and this goes from the ground to about 20 kilometers in altitude. And this is where we have the weather that you and I normally think of, so like thunderstorms and hurricanes and snowstorms and that kind of thing. And this is also where airplanes typically fly. The next layer up is called the stratosphere. This is the highest altitude that weather balloons are going to fly to. And this is also where the ozone layer is located. The layer above that is called the mesosphere. And then finally, we have the thermosphere. And the thermosphere runs from about 90 kilometers in altitude up to about 700 kilometers in altitude. And this starts to be some of the more tenuous part of the atmosphere, but very significant because things like the space shuttle and satellites fly in this region. And then I've marked on here gold, and that's not actually where gold is orbiting, that's where gold is sensing. So this is an emission region at about 160 kilometers in altitude. Now we have different things that are coming up from below and interacting with the thermosphere, but we also have things that are coming in from above and interacting with the thermosphere. So from above, we have solar extreme ultraviolet radiation absorption. So in this picture, it shows different types of light that can come from the sun and what layers of the atmosphere that the light can reach. So if you look at the visible and IR light, it gets all the way down to the surface of the Earth. but the extreme ultraviolet radiation only makes it into the thermosphere, where it interacts with some of the air that's up there. We also have particle precipitation, and this is kind of from different things that are spewed at us from the sun, and they get directed into the polar regions of the Earth, and they can interact with the air and cause illumination events, kind of like the aurora and that sort of thing. There's also a phenomenon called Joule heating, and this is where you have a current that runs through our atmosphere and heats the atmosphere as it goes along. Then from below, we have the dissipation of upward propagating waves, and these waves come from different tropospheric and middle atmospheric processes. And really, in the last decade, we've had evidence that has shown that terrestrial weather, so that those thunderstorms, those hurricanes, can really significantly influence the ionosphere and thermosphere. So those waves and tides come from a variety of sources, have a variety of different features. And we usually classify our waves and tides by their scale and their restoring force. And as you can see in this picture, it's actually kind of a messy, complicated system. So we have gravity waves coming up from below, we have tides, we have planetary waves, and then those get up higher up in the atmosphere, and then they start interacting with things like aurorally generated waves, different sorts of plasma flow, and that sort of thing. But what's key here is that the primary mechanism through which energy and momentum are transferred from the lower atmosphere to the upper atmosphere is through this propagation of waves. And that's why we care so much about it, is because of this energy and momentum transfer. So there are several kinds of waves that we think that might be existing in the thermosphere. The first one is a type of wave called a Kelvin wave. And this is an inertial wave that needs some sort of boundary, so a waveguide like the equator, in order to propagate. You also see these types of waves in the ocean along coastlines. But in the thermosphere, they have timescales of tens of days, and they are an entire planet-wide phenomena. We also have Rossby waves, and these are waves that have timescales, again, of tens of days, but they're smaller in horizontal scale. So these are hundreds of kilometers in size. We're not really sure if these types of waves are actually going to propagate into the thermosphere and be observable by GOLD, but it is something we'll certainly look for. And if we do see them, it'll be pretty exciting. The next type of wave is called a thermal tide, and these are forced by periodic heating from the sun. And so their time scales are fractions of a solar day. And then these are planet-wide phenomena. And then the last type of wave is called a gravity wave. And these waves have gravity and buoyancy as its restoring force. They're very short time scale, so minutes to hours, and pretty small horizontal scale. So we're talking tens to hundreds of kilometers in size. So they're a very local kind of wave. So in this talk, we're going to focus mostly on the thermal tides and gravity waves, just because they are some of the most significant sources that basically connect the upper atmosphere and the lower atmosphere together. So first we'll talk about thermal tides. And just to be clear, these tides are different from gravitational tides that you might have heard of before, like the lunar tide, in that they are thermal, and that they are from the periodic heating of the atmosphere by the sun. It doesn't have anything to do with gravity. The heating of the atmosphere and the sun comes from different regions. So if you look on the left-hand side of your page, you can see that you have heating down in the troposphere from latent heat release. So this is when water vapor turns back into water, and you have heat release, and that can cause a tide. Up in the stratosphere, there is ozone heating, and this can cause, again, more tide activity. Up in the thermosphere, there is extreme ultraviolet heating of O and O2, and this is where heating in the thermosphere happens. So if you can imagine on the right-hand side, heating from the sun is a function that looks like this. So you have a very sharp transition from day to night, so at sunrise and sunset. And if you were to describe this with a series of other functions, you would first calculate the mean, and then you would calculate a diurnal component, which means once per day. And then you would also calculate a semi-diurnal component, which is a fancy way of saying twice per day. As scientists, we mathematically calculate it, and this allows us basically to calculate a tide for every altitude and latitude on the Earth, given a zonal wave number. And zonal wave number is a way of saying how many peaks and valleys are there along a circle of latitude. So we observe these tides in measurements of, say, temperature and wind, but you can also do it with other observational techniques. With gold, we're going to try and do it with O to N2 ratios. And we have two main types of tides that we talk about. These are migrating tides, which are tides that follow the apparent motion of the sun. And then we also have non-migrating tides, which is basically all the other kinds of tides that are out there. So if you ever are looking at some of the literature, some of the standard nomenclature works like this. It's a combination of letters and numbers. So the first letter tells you how often per day it happens. So diurnal, D, semidiurnal, S, and terdiurnal, T. The next letter denotes whether it's westward or eastward propagating. So you have W for westward and E for eastward. And then the letter, or the number, the final number, basically tells you how many peaks and valleys there are around a latitude circle. So for example, the DE3 tide is the diurnal eastward wave number 3 tide. And this is actually a pretty important tide in the thermosphere. And it's a driver of what looks like a wave 4 structure in local time when you're observing from low Earth orbiting satellites. But it's excited in the tropical troposphere by deep convective systems, so large thunderstorms and that sort of thing. And one of the reasons we look at it is it's a big source of the variability that we see in the mesosphere and lower thermosphere. So you can get up to a 30K change or 20 meters per second change. So this is a small movie of what the different tides actually look like, the different tidal components that I was just talking about. So you can see on the top row, all of these are westward tides, so they're moving with the apparent motion of the sun. And then on the lower row, we see eastward moving tides, so those are the non-migrating tides. So if you look at, for example, compare DW2 and DW1, you can see that there are twice as many peaks and troughs in DW2 as DW1. So that kind of helps explain the 1 versus 2 in the nomenclature. And then if you look at the lower right-hand corner, you'll see the DE3, which is the diurnal eastward wave number 3 tide. And you can see how significant it is. It's very large, and it's a very prominent feature of the thermosphere. So next we're going to talk about gravity waves. And first I want to clarify that these are not to be confused with gravitational waves, which was discovered by the LIGO team and has to do with black holes colliding and that kind of thing. These are atmospheric waves, and gravity and buoyancy are the restoring force for these type of waves. So you can imagine if you have an air parcel and somehow by some mechanism it gets moved up in altitude, all right? Gravity is going to pull that air parcel back down, but it'll overshoot and go further down. At that point, buoyancy will boost it back up. And this process repeats, and you end up with a wave. These are small local scale waves. And again, they play a really important role in connecting the lower atmosphere with the middle and upper atmosphere. So as the wave grows, propagates up in the atmosphere, the amplitude will actually grow because the air density is decreasing, which is due to conservation of energy, and eventually the wave will break, just sort of like a wave on the beach. And when it does, it'll deposit the momentum that it's been carrying, say eastward or westward momentum. And that momentum can actually change the direction of the winds, or it can generate entire circulations in the atmosphere. And that's one of the reasons we really care. So you probably are wondering what kind of mechanisms can cause the air parcels to move up and down. The first one is simply wind over, say, mountains or islands in the middle of the ocean. We call that orography. Another method is through deep convection, so very large thunderstorms or hurricanes, and it looks just like a pebble thrown into a pond when you see these type of gravity waves. And next I'm going to show you a little movie of some of these gravity waves in the thermosphere. This is a model that was done by Hanli Liu and company, and using a model they were able to basically show what they think gravity waves are going to look like in the thermosphere. And hopefully this is what we'll be observing with gold. And in the middle, when the video loops back around, you'll see a large series of concentric circles right now. And that's actually due to a typhoon that was off the east coast of Australia. And as you watch it, you can see different overshooting behaviors and all sorts of other waves going to the left, to the right, and you can see what kind of scale they are compared to the land masses. But it's a great little video. So unfortunately, this gets a little complicated because we have nonlinear wave interactions. And what I mean by nonlinear is that when you have two waves and they mix together, the result is not a simple addition of the two waves or addition of the waves. It's some other function, so maybe multiplication or some trigonometric function. So the way it works is you have two primary waves. Say wave one is a tide, a thermal tide, and wave two might be some sort of Kelvin wave. They propagate up into the atmosphere, and then they mix in some nonlinear forcing region, which is mathematically how we show that. And then out comes two other waves, a secondary wave one and a secondary wave two, where the first wave is a sum of cosines and the other wave is a difference of cosines, which is all fancy way of saying that these are not linear functions. And this is one of the things that adds complexity to the entire system. So next, let's talk about how we observe some of these waves. The first methods were based around ground-based methods. So we can use incoherent scatter radars. And these can measure the mesosphere and lower temperature, lower thermosphere temperatures and winds between about 100 and 120 kilometers, but they don't measure continuously. Another type of system is a resonance LiDAR, which I spent a lot of time operating in my grad school days. And this is a laser that you can basically use to measure temperature and winds, but the systems are pretty complex and we haven't figured out how to run them continuously. We can also use MF and meteor radars to get winds between 80 and 100 kilometers. And lastly, we can use passive optical methods. So some of the advantages to these systems is that you're able to distinguish waves over a short time period. And you're going to get a lot of information on the vertical structure, which can be important for deriving different quantities that concern the energy and momentum transfer of the waves. Unfortunately, there's a couple disadvantages as well. You're going to lack information on the latitude and longitude structure of any of these waves. And you're going to have an inability to distinguish between global and local scale waves. So you won't be able to tell what's passing overhead. Is that a really large Kelvin wave or is that a really small gravity wave? And I just want to stop here and share one of my favorite historical side notes about studying the atmosphere. And back in the 40s and 50s, they had theorized that these thermal tides were up in the mesosphere and thermosphere, but this was before they had satellites that could really measure this region, and it was too high for airplanes to go up there. So they came up with this idea that's still amazing to me today, where basically they took a rocket and they loaded it with a bunch of grenades. And then they launched the rocket and ejected the grenades out the side. And on the ground, they had these microphones, and they would listen for the boom to happen. And basically, from these grenades exploding, they were able to determine the wind speed and direction of the mesosphere and lower thermosphere. And they didn't just do this once. They did this multiple times all around the world. And from this, they were able to actually derive some tides, and they were actually got pretty close to what we think of as the thermal tides today. So another method of getting at some of these wave fields is using a low Earth orbiting satellite. So for example, NASA's upcoming mission ICON, which is the Ionospheric Connection Explorer, which is the quickly moving little dot on the video. And the thing about this type of orbit is that you have changing longitude and latitude continuously. And some of the advantages of this is that you have really good longitude and latitude coverage. So lower the inclination, which is the angle between the orbit and the equator, the more rapid the orbit precesses with respect to the sun. And this allows you to get a higher sampling rate. Unfortunately, it has some disadvantages. So for example, one of the problems with the sampling is that you're never going to be able to sample the same air mass twice within 24 hours. Another problem is going to be aliasing. And aliasing is basically when you misidentify the wave or tide that you're looking for. And this has to do with how you sample the atmosphere. There's another kind of orbit that we can use to observe Earth's atmosphere, and it's called a geostationary orbit. This is an orbit where the satellite actually moves and in its orbit at the exact same speed that Earth is rotating. So from the ground, it appears that the satellite is hovering overhead. And from this, you get to look at the same region on the Earth continuously. This is the orbit that gold is in, and we haven't ever gotten this view of the Earth before with this type of instrument. So one of the advantages is that we're going to get local time coverage. So we get to observe as these waves and tides develop and change in place. So we'll be able to separate time and spatial variability. So we'll be able to tell if that's a gravity wave or that's a Kelvin wave moving through our field of view. There is a disadvantage, and this is longitude covered. So we aren't going to be able to see the far side or the dark side of the Earth. We only get to see about 140 degrees of longitude at a time. And this can complicate our derivation of thermal tides. So I want to just end with some of the early initial observations from gold. We recently turned gold on. It's still going through scrub and calibration and some other checkout things, but we did get some initial data. This is the 135.6 nanometer channel, which is in the extreme ultraviolet. And what you can see here is the terminator line, which separates the night side on the left from the day side on the right. And then we were lucky enough to be observing during a geomagnetic storm. And because the sun has been so quiet, we haven't been able to see that many of these. But what is exciting about that is that meant we got to see some aurora. And you can see the aurora on the night side in the polar regions. So hopefully soon, once we get to start taking real science data, with gold, we will get to be able to do some more analysis and actually be able to pull out some of the wave and tide information that we're so interested and excited to be getting out of that. So just to conclude, these are some of the main points I hope that you take away from this webinar. First of all is that variability in the thermosphere is due to both incoming energy from above and also energy from below from atmospheric, tropospheric weather. Thermal tides and gravity waves connect the lower and upper atmosphere through transfer of momentum. And those thermal tides are driven by periodic heating of the atmosphere by the sun. And gravity waves are a type of buoyancy wave that kind of looks like a pebble that's been thrown into a pond. And lastly, we can use different observational techniques to sense waves and tides from the ground and space, and that gold is in a geostationary orbit, so we get to stare at the same side of the Earth all the time. And with that, I'll see if there are any questions. So thank you.
Thank you, Katelynn. Any questions? If you do have a question, you can type it into the chat, and you're also able to unmute your microphones if you want to ask a question through your speaker on your computer. If there are no questions, I'm just going to, again, say thank you to Katelynn Greer for this wonderful summary of the forcing from below and the gold mission.
Yes.
Very interesting. And we will have at least one more gold webinar in either next month or in November. And by then, we expect the instrument to be returning real science observations, just like the one that was shown here, but even more involved and exciting. We'll have a more comprehensive view of what kind of data products will be coming down from the mission. So that next webinar will be about the science data pipeline and how we actually get the data from the gold instrument, which is a hosted payload on a commercial communications satellite in geostationary orbit, how we get that down to the ground station and here to the Laboratory for Atmospheric and Space Physics, which is kind of where the raw data comes, and then we actually send it from here to the University of Central Florida, where the Science Data Center for Gold is hosted. And then they do additional processing and validation of the data from that point on. So I'm hoping that our lead data person here at LASP, Karen Bryant, will be able to join us for that webinar. So stay tuned and pay attention to your typical outlets for information on when that'll be. And we'll see you next time. Last chance for any questions, if anyone has any questions. We did see there's one comment that just says, thanks, this has been very interesting. So with that, I'm going to go ahead and sign off. And this video will be posted on the Gold website, which is in the chat, if you're interested in sharing that with others who are not able to attend, or if you'd like a recap for yourself in the future. Thanks for joining, everyone, and we'll see you next time.